Welcome to UV Physics Academy. So here we are discussing quantum algorithms. This is the second part. In this, we are going to discuss about one of the protocol, that is quantum teleportation. So what is this quantum teleportation? First, let me explain the task. So let us suppose here we have two persons. Let us say A and B. Now here A wants to send quantum information, that is, let us suppose psi equal to alpha 0 plus beta 1. Okay, so they want A wants to send a quantum information state, that is psi is equal to alpha 0 plus beta 1 from one point to another point. Okay, but before that, so there is one Bell state, let us suppose beta xy. Now in this I am taking this as a beta 0 0, which is 1 over root 2 0 0 plus 1 1, right. So already one Bell state is created. So from this Bell state, A taken this first two qubits, that means you can take this as A and this is also A, first one, or let us suppose like this, and B taken second qubits of a Bell state. So that is nothing but this second 0 and here second 1. These two qubits are taken by B. So right now A is having one psi quantum state, psi is equal to alpha 0 plus beta 1, which A wants to send from one point to another point. And first two qubits of that Bell state, that is 0 comma 1. This is what A is having. And right now B is having the second qubits of this Bell state, that is 0 comma 1. Fine. So I hope you understand the task. So one Bell state is created. From that Bell state, first two qubits are taken by A and second two qubits are taken by B. And A wants to send a quantum information psi equal alpha 0 plus beta 1 from one point to another point through classical channel. So what is this classical channel means? He want after making a measurement, A should inform to B whatever he got that measurement. For that he will use some classical channel. Then B will do some operations on his own state, and finally he will get back to this psi alpha 0 plus beta 1. So this is the problem. Okay, so finally I hope you understand what is this teleportation. Sending quantum information let us suppose that is the psi equal to alpha 0 plus beta 1 we are sending from one point to another point through classical channel. So no need to get confusion about this, what is this classical channel, because first A will do some measurements. Okay, A will do some operations. After that he will measure his two qubits. Then whatever the measurement value he got, he has to inform to B. Then B will do some proper operations on his own state, and finally he will get back to this initial state, that is a psi equal to alpha 0 plus beta 1. So this is the task. Now let us take the quantum circuit corresponding to this quantum teleportation and how to solve. Let us discuss. Right. So here we have taken three qubit states. Okay. So here these are first two. So I am taking here 0 and this is also 0. Here we are creating a Bell state. So head mod operation and after that a C naught operation. With this we are getting this beta 0 0, which is 1 over root 2 0 0 plus 1 1. Remember, so these first two qubits are taken by A and this second two qubits taken by B. Fine. And here whatever the state we want to send from one point to another point, that is a psi equal to alpha 0 plus beta 1. Fine. Right. So after that A will do some operations, that is the first C naught operation. Here this is the C naught. Okay, C naught operation on his first two qubits, and after that one head mod operation will be there. So then make a measurement. Then we are informing this through a classical channel. That means once you make the measurement, these two qubits, you may get 0 0 or 0 1 or 1 0 1 1. Then this information passed to B through some classical channel. Okay, so after that this B will do some measurements on his state, that is here X and control X, I mean C naught, and here we have control Z operation. Like this. Okay, so then whatever the final state will be equal to that this one initial state. The state received by B is equal to this psi equal to alpha 0 plus beta 1. So this is the quantum circuit corresponding to quantum teleportation. So let us solve this circuit. Okay, so here we have initial state, this is psi and beta 0 0. So that's why alpha 0 plus beta 1, actually this is the tensor product, 1 over root 2, this is 0 0 plus 1 1. Remember, these are two, I mean this state is this state belongs to A, and here the first one is also A, and here the first one is A, and here the second one is belonging to be this B. Fine. So let me find this tensor product. This is nothing but alpha, of course, 1 over root 2 alpha 0 0 0 plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1, like this. And don't forget this point, these first two qubits belongs to A and the last one B qubit. Fine. After that we have this C naught operation, this one C naught operation on the first two qubits of A. So this is the C naught operation of A. Okay, so then I am performing this C naught operation of A, then what we will get, 1 over root 2 alpha. Please observe the first two qubits of A. In the first state 0 0, that's why control bit is 0, that's why second qubit no change, 0 0 only, plus alpha. Here also control bit is a 0, so that's why 0 1 1 same, but here the control bit is 1, so that's why 1 target bit 0 flip to 1 plus beta. Here control bit is 1, so that's why 1, the next target bit will become 0. That's it. So this is the state after C naught operation of A, and then one head mod operation is there on the first qubit. So this is the head mod operation on first qubit. First qubit means here this one, and we know this H operates on 0, will get plus, which is equal to 1 over root 2 0 plus 1, and H operates on 1, this is minus 1, sorry, minus 1 over root 2, 0, minus 1, diagonal basis. So by using this, I mean after the head mode operation on the first qubit, we will get 1 over root 2 alpha plus 0 0 plus alpha plus 1 1 plus beta minus 1 0 plus beta minus 0 1. Right. So let me take that plus state and minus state and substitute here. So then it will become 1 over root 2. Oh, I'm sorry. Here once you while you are substituting plus and minus, one more root 2 is there. So that's why here it becomes 1 by 2 alpha. If you substitute plus, this will become 0 0 0 plus 1 0 0. Next again alpha. Now again I am substituting plus, a diagonal state plus state, that is 0 1 1 plus 1 1 1. Okay, already here two qubits 1 1 are 1 1 are there, so just introduce that plus state plus beta. Here we are writing minus state, so which is a 0 minus 1, that's why it become 0 1 0 minus 1 1 0, sorry, one more is there, plus beta plus beta. Here I am substituting minus, that is 0 0 1 minus 1 0 1. Right, and don't forget this. So here these two qubits A, this belongs to A, first two qubits belongs to A, and the second qubits sorry, the last one belongs to B. This one don't forget. Now we would like to separate these first two qubits of A. Why? Because we want to do the measurement. Okay, so let us separate this. For that, let me copy the last state. Right, so again I have taken that last state here. Now let us separate qubits states of A and B. Okay, so now I am taking first two qubits of A, that is 0 0. Okay, so these belongs to A, and the remaining alpha 0, please carefully observe this one, and similarly here this one. Okay, so then we will get alpha 0 plus beta 1. Next I am taking this 0 1, so where it is here and here, please carefully see those two. Then this is alpha 1 plus beta 0. Next I am taking next I am taking a plus 1 0, which belongs to A. So where is this 1 0 state? Here and here. Right, so then it is alpha 0, but here it is a minus a beta 1 plus 1 1 A. So where is this 1 1? So here we have alpha, and here we have a beta. So this is alpha 1 minus beta 0. Fine. Now let us make a measurement on this measurement. Okay, so once you make the measurement, so this is let us suppose measurement of A. So once A make measurement, he will get a 0 0, a 0 1, 1 0, 1 1. Okay, now I am taking the state corresponding to B, B state. or state of present state of, let us say, let us write present state of B corresponding to 0 0 measurement. So B got this state alpha 0 plus beta 1. So once he passed the information of that measurement done by A, so that he got a 0 0, then this B will perform, this is the operation by B. So just he won't do any measurement, that means he won't apply any gate, that is I. Finally he will get alpha 0 plus beta 1. Next he got this, I mean he got 0 1 and passed this information. Then the present state of B is alpha 1 plus beta 0. So once he know that after making the measurement by A he got 0 1, okay, 0 1, then immediately he will apply X operation. So that is alpha 0 plus beta 1. Next again pass the information, that is A got 1 0. So then the present state is alpha 0 minus beta 1. So once B knows that A got the value or A got the measurement values 1 0, then immediately will apply Z. So this become alpha 0 plus beta 1. And the next if A got the measurement as result as 1 1, the present state of B is alpha 1 minus beta 0, then he will operate both X and Z. So 0 to 1 flip, and 1 will get a phase factor, extra phase factor. So this become alpha 0 plus beta 1. So this is the state A wants to send to B, and finally the information, the quantum information, reached to B. So this is quantum teleportation. Okay, so here I want to discuss the same quantum teleportation circuit in a different way. That means by using the decimal notation, how to solve this circuit easily. So here we have already solved the circuit, but we have completely used the binary notation. So what I am saying is, if you are proceeding with the decimal state notation, it is a bit easier to solve this mathematics. Let us try. I hope you understand. So if you already attended that earlier decimal notation which I explained in the quantum circuits videos, you will understand. Otherwise, once go through that method, okay, right. We are going to solve this quantum teleportation circuit by using a decimal state notation. Right. So here I have taken this circuit, quantum circuit. So just this is an alternate way. Okay, if you are interested, you can proceed with this. Otherwise, already I have explained that binary notation. So 3 qubits are there. First, let me explain one more time what is this decimal notation. So here, whenever we have decimal state notation. So for example, if you have 2 qubits, okay, so then you have to represent these states 1 and 2. Actually, what is that 1 and 2? If this qubit is on, you will get 1. If it is off, 0, like that. So q1, if it is on, will take value 2, otherwise 0. So if you have 3 qubit states, so that's why 1 2 4. Okay, actually 2 power 0, 2 power 1, 2 square, that is what I have taken. If 4 qubit states are there, you can take 1 2 4 8. Okay, right. So now let us come back to the circuit. Here we have 3 qubit states, that's why I'm taking 1 2 and 4. Now listen carefully. So here we would like to send the information, that is a psi equal to alpha 0 plus beta 1. So forget about that binary notation and all these things. Here, what is the meaning of that 0 and 1? So generally 0, I'm taking it as an off state, and 1 as an on state, something like that. Okay. So then here we are sending this psi, this one, fourth one, that qubit state, 4, decimal value is a 4. So that's why this is nothing but alpha 0 of If it is on, beta 4. Okay, if you are sending that psi here, it will be 0, alpha 0 plus alpha beta 1 only. If you are sending that psi here, we can take alpha 0 plus beta 2, because we are sending at this point, I mean at this qubits. So just a alternate method. So let me check whether we will get the same answer or not. So I don't know whether this type of idea is right or wrong. First I got an idea and just implementing this. So here we have, finally this is a psi a beta 0 0. So beta 0 0 is nothing but 1 over root 2. So here decimal state notation 0 plus 3, because 0 0 is 0 and 1 1, that is the 3. So don't forget to represent. Here we have 2 qubits. So this is nothing but alpha 0 plus beta 4, and this is a 1 over root 2 0 plus 3, and here there is no tensor product. So earlier we have a tensor product, and here just add, let me do this completely, then you will understand. 1 over root 2 alpha 0 plus alpha 3 plus beta 4 plus beta 7. That's it. Okay, so no need to get tension. Why, how you got this 7, I will tell you. So 4 means on, right? So here this one, this is on. Here 3, this I told you already, here 2 qubits are there, that is a 2. Okay, so here both are on 1 1. So that's why 1 1 1 can be written as a 7. So this is the this is what I have taken. Fine, let us proceed. Now after this we have some C naught operation. Okay, so I hope everybody attended that quantum circuits, and here this is nothing but x of 422, that's why 4 comma 6, and the remaining is 1 5 comma 7. So here the operations 4 comma 6 and 5 comma 7. Let me operate this. This become 1 over root 2 alpha 0 plus beta 3 plus beta 6 plus beta 5, because the 7 become 5, 4 become 6, right? So once you got this state, again we have to apply head mod operation. So let me write this a head mod operation, the decimal notation operations. H is on 4, that's why h of 0 comma 4, and this is a h of 1 comma 5, because we have to add 1. Next these two we have to add 2, that is a h of 2 comma 6 and a h of 3 comma 7, right? So this 0 become linear combination of 0 and 4, off on off on. This complete notation I have explained in the circuits. So this is a 1 over root 2 alpha 0, that is off state, that's why 0 plus 4. So beta 3 is off, that's why 3 plus 7, and plus, oh I think here I make a mistake, alpha, I'm sorry, that is alpha, because alpha, right? So here also alpha and plus beta. So this is 6 is on state, that's why 2 minus 6 plus beta 5, that is also on, 1 minus 5. Good. See here I am not making any measurement, just I am solving the quantum circuit, and let us check what we are getting finally. And after that we have one C naught operation. Okay, so let me write this a C naught operation. This is from 2 to 1, 2 to 3, and this is, we have to add 4, so that's why 6 comma 7. Next control Z is there. Okay, that is a 4 to 1, 4 comma 5, and we have to add 2, that is a 6 comma 7. Remember, X will flip and Z will add one phase factor if it is on state. This is off and this is on. First numbers are off, second numbers are in on state. Fine. So let us apply C naught, then we will get 1 over root 2 alpha 0 plus 4, no change, I am applying only x operation, plus alpha 3 become 2, 7 become 6, plus beta 2 become 3, 6 become 7, plus beta 1 is as it is or 5 is as it is. And after that I am applying this a control z operation, so that is a 1 over root 2 alpha. So it will add phase factors to 5 and 7 and remaining things are same, 0 plus 4 plus alpha 2 plus 6 plus beta 3 plus 7 plus beta 1 plus 5. That's it. So this is the final state I got. Let me take this state again. Right. So one more time I'm saying, just I'm using this decimal state notation to solve the circuit easily. So let us check finally whether we are getting the same answer or not. But I'm not sure whether we can do in this way or not. Okay, so finally we got this. Now I'm going to separate this A and B state. See that A state corresponds to that 2 and 4 qubit states. That's why what are the possible decimal states of A? If both are off, that is a 0, 2 on, 4 0, I mean 4 off, that is a 2, and 2 off, 4 on, it is a 4, if both on, a 6. So we have to separate 0, 2, 4, 6. No need to get tension, this 0 is a 0 0 only. 2 stands for whatever we have taken there, 1 0. Yeah, sorry, 0 1 0 1. This 4 stands for 1 0 and 6 stands for 1 1. That I will explain, no need to get tension. So now here I am going to separate this 0. Here we have 0. Okay, so this can be written as 0 plus 0 plus 0, and somewhere here 1 can be written as 0 plus 0 plus 1. Carefully observe, these first two things are off. That's why I'm writing. If you want, you can write binary notation, no problem. Okay, let me write decimal only initially, 0. Okay, and alpha, so what is the remaining? 0. Here what is the remaining? Beta 1. Okay, so please proceed. Okay, next I'm going to separate this here 2 is there, so this 2 can be written as a 0 plus 2 plus 0, because a 0 2 0. Okay, and somewhere, yeah, here this one, 0 plus 2 plus 1. Now I am separating 2. Okay, or if you want, you can write this is sorry, so this is off on, off on. So if you want to write the binary, you can write it as a 0 1. That is what I am saying. 1 on means 1, off means a 0. Let us take like that. If you want to convert from decimal to binary, you can take like that. So 2. So here also I am getting alpha 0 plus beta 1. Okay, so if you want to represent this in the binary, you can take it as 0 0. If you want to write 2, off on, that means 0 1, which exactly match with the earlier answer. This belongs to A. And next I am separating the 4. Okay, so 4 if I separate, so 4, where is this 4? Now carefully check here. How you will get this 4? 4 plus 0 plus 0. Now tell me, this 4 is on, 0 is off. That means in our binary notation, that 4 0 is nothing but 1 0. Okay, ready. So, and one more 4 here 5. So this is 4 plus 0 plus 1. Now here I am separating this on, off, 1 0. So this is alpha 0 plus beta 1. Next again I am separating 6. That means both on, So here is a 6, 4 plus 2 plus 0, and here is a 7, 4 plus 2 plus 1. Now I am going to separate both on states. 4 plus 2, that is 6. Here it is nothing but 1 1, alpha 0 plus a beta 1. So here this states corresponds to B. He got the information initially whatever A wants to send to B. Actually here just an alternate way to solve this quantum circuit, because I have already solved the quantum circuits by using decimal state notation. Then I got an idea, why don't we solve these quantum algorithm circuits by using this decimal notation. Just a small try. Okay, so I hope you understand. If there is any a mistake, or if this is the wrong method, so please let me know. So but finally we are getting the answer. The only assumption what I am doing is, so whenever here I would like to convince what is this decimal state notation. If you have these two qubits, let us suppose this is 1 and 2. So here what I am assuming is, so possibilities both off, that is a 0. So on, off, that is 1. This is on, this is off, 2, both on, 3. Actually these four are nothing but our base states, 0 1 2 3. In the decimal notation, in the binary notation, we will write 0 0 0 1 1 0 1 1. So this is what I have taken, I mean in this method what I have assumed. Okay, so thank you, and we will meet again in the next video.